I just want to thank everyone for coming out tonight. So AstroTours, this is a monthly event that the graduate students here at the University of Toronto put on to share our love and interest in astronomy and all things astronomy. So you may have noticed that we passed out feedback forms when you're coming into the room. We really value the feedback that you give us. Again, we're a student-run organization, and this will help us to improve and give the best AstroTours that we possibly can. So for the afterwards, we have a couple of different things. We have planetarium shows. Some people have already booked tickets. We also have tickets that will pass out. So do you want to bring in the planetarium ambassador? Make sure that I can point him out to everyone. So we have tickets that people have already signed up for. We sometimes have drop-in spaces, so you can check in with the planetarium ambassadors. And then there's a 9:10 show, a 9:30 show, and a 9:50 show. And we also just have tickets to pass out. So if you've already booked tickets online for the 9:10 show, we have Victor up here who will direct you to the meet point just in front of the elevators. And then after the talk for the 9:50 show, the tickets will be handing out in Ariel up here. And these two are our planetarium ambassadors. You can ask them any and all questions about available spots for the planetarium. And we also have things like we have a worldwide telescope, we have 3D printed telescopes. So if you go to the elevators and head up to the 14th floor, we have refreshments and all sorts of things that you can do after the talk as well. And just an announcement that, so everyone is aware, Queen's Park Station is closing at 10 p.m. tonight. Normally we don't make transit announcements, but I feel like that's an important one. There is, of course, St. George Station for the subway if you walk up St. George Street, and there are a few others around. So if you are unsure about how to get to a subway station after 10 p.m., please do ask one of the volunteers, and we'll be happy to do our best to help you navigate getting back. But with that, we'll get started here. So I'm really pleased to present Catherine here, Catherine Woodford. She is one of our graduate students here. She's in the Department of Physics, and she is working on her PhD also with the Canadian Institute for Theoretical Astrophysics. And so she is a member of the Simulating Extreme Spacetimes collaboration, and we'll bring up your talk here as well. I'm just going to plug this in. Sure. But she is also really involved with the outreach here that we have at the University of Toronto. She gives lots of planetarium shows. If you come to the AstroTours before, you probably had a planetarium show with her. So I'm very excited to announce Catherine. So let's give her a warm welcome for her to be here.
All right, well, thank you guys for being here. It means a lot to especially have my students from the Abelard private school over across the way. It means a lot to have you guys out tonight, and I always appreciate the regular AstroTours people for coming out. So as Elisa just said, my name is Catherine Woodford. For most of you guys in the audience tonight, I am Miss Woodford. Good. Regardless, as was just said, I am a third-year PhD candidate here in the Department of Physics. I work in the Canadian Institute of Theoretical Astrophysics, which kind of sits across the physics department and the astronomy and astrophysics department and does theoretical astrophysics. So that's all good. So what I'm here to talk to you about tonight is partially what I do, but also what my group does, what my collaboration does, and also what the astronomy world is kind of buzzing about right now, which is gravitational waves, which we are now calling the sirens of the universe. And I actually don't know who said that first. Maybe it was Kip Thorne. I don't know. But regardless, we have candles for the universe. We have supernova. We have things that we can see in light. And now we have gravitational waves being the sirens. So the first thing I wanted to bring up was what we actually do here at CITA. So what I'm showing here is a simulation of a binary black hole. So two black holes, that's what these dark things are going around. The colored parts you see underneath them are the spacetime. And this part down here you see that's kind of advancing as we go along the simulation is what we call a waveform. And I know a lot of those words just went whoop. And that's okay, because we're going to explain what all this means. But what I really wanted to show you first is give you some context into what I do and what we do here at CITA, as well as in the Simulating Extreme Spacetimes collaboration. So essentially, we simulate these really intense objects, and we slow down the movie here to show these two black holes kind of merging together. It's not easy to simulate, as I'm going to discuss. It's actually quite difficult, which is why we have so many people working on it all the time, running the simulations and trying to make them better. However, simulating extreme spacetimes, SXS, is not just CITA. There are a number of institutions that work on it and look at this rippling in spacetime that's moving out from the simulation here that's called gravitational waves. So in particular, all of these places are listed, but again, Canadian Institute for Theoretical Astrophysics is a big one in that collaboration. So now I'm going to get into, okay, well, what is a black hole? What is a binary black hole? Because maybe we should know what a black hole is first. What does the spacetime have to do with anything? And what does that waveform mean? What did all those squiggles at the bottom of the screen do? So in order to talk about that, the first thing we're going to need to kind of think about, kind of get our heads wrapped around, is the idea of gravity and the idea of spacetime. So first we're going to have to think about, okay, well, what is spacetime? So normally when we think of spacetime, we think of it as everything around us. We are currently sitting in spacetime. It's our three-dimensional, or if you include time, or four-dimensional space, our length, height, width, and time, moving in one direction. However, we can take a step back and think of it as a two-dimensional sheet for right now, which is what we have listed here as our green grid. So the idea here is that it acts like a rubber sheet. It gets bent by matter. So Einstein had kind of an analogy he liked to use to describe how this stuff reacted to each other. And he said, okay, matter tells spacetime how to bend, and spacetime tells matter how to move. So it's the bending in spacetime that makes things move. So it's the bending of the spacetime around the sun that causes the Earth to orbit around it, and other things orbiting around other parts, how galaxies accrete things, and yada, yada, yada. However, we want to think about the idea of something bending in the first place. So if something has matter, has mass, it's going to cause a bend in spacetime. You're causing a bend in spacetime. You're also causing a bend in spacetime. You're causing a bend in spacetime. I'm causing a bend in spacetime. Maybe my bend in spacetime is larger than someone else's, probably larger than Miranda's. And maybe someone has a larger bend in spacetime than me. It has a lot to do with mass, which we normally weigh in kilograms. So the more mass you have, the larger your bend. However, we also need to think about the density of an object, or what you might like to think of as compactness. So I'm going to stick with the word density. So how much mass we can fit into a space. So let's think about lead and styrofoam. Lead is more dense than styrofoam. So if I took my rubber sheet of spacetime and I put a lead ball in the center, probably dip pretty far, right? If I had a rubber sheet and I put a lead ball on it, it'd probably dip pretty close to the floor. Let's say I took a styrofoam ball of the exact same weight. Has the same amount of mass. However, putting that styrofoam ball on the rubber sheet is going to cause that bend to look a little different, because the styrofoam ball is going to be huge to have the same weight as that lead ball. If I have a lead ball like this, the styrofoam ball is going to be massive to get the same amount of mass in there. So it's not just the amount of mass you have or the weight that you have, it's how much of it in a small space, or your density. So we can kind of think of it like this picture with the sun and the Earth. The sun, being a star, is more dense than the Earth, being a planet, and especially a Terra planet, rocky planet. So things like the sun, stars, cause space-time to bend a little bit more than planets, not just because they are more massive, but because they have a higher density as well. They can fit more mass into a small amount of space. Okay, so that explains a little bit about how space-time is bending. But things don't just sit in space-time, right? Space-time also tells matter how to move. So maybe we want to think about how things are moving in space-time as well. And that's where we get behavior kind of like this in our two-dimensional sheet of space-time. So what this shows are two very dense objects, things called neutron stars. And I'll tell you what neutron stars in a second, but I just want to explain the video first. So now we have things that are very, very dense, causing a very deep well, a very deep pull in space-time, a deep bend. But then they also move, because space-time is telling them to move. So especially when they're close together, they interact with each other. One bends at space-time, and the other one kind of follows around, and then they end up orbiting. That's how a lot of orbits happen. Most, actually, all. So for these ones, if you can also think about maybe a pond instead of a rubber sheet, and we have two sticks in our pond, as they orbit around, as we moved our sticks around in our pond, we're probably creating waves, right? We can imagine that. If we move a stick through a pond, it's going to create ripples that'll move out. Same thing happens in space-time. So we have a couple of ingredients here. We have mass, but not just mass, but a lot of density, a lot of mass in a small space, creating a very significant bend in space-time, and then also moving through it. And that's what creates these ripples in space-time. What causes gravitational waves. So matter moving through space-time causes gravitational waves. So we're going to do an experiment now, just to kind of solidify this in our mind. I want everyone to hold out their arms. And I'm going to ask you to not hit anybody when we do this. Please be careful. Yeah. So now we're going to shake our arms back and forth. Shake, 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 shake as fast as you can. As fast as you can without hitting anybody. Do it, do it, do it, do it. Shake, 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 shake. Okay, stop. Stop, stop, stop. So your arms have mass. And we just moved them really fast through space-time. Did we create ripples? Who thinks yes? Who thinks no? Doubtful? Okay. So we did create some ripples in space-time. But our arms don't weigh very much, and we're also not all that dense. I mean, we're not as dense as lead, as my previous example, and we're definitely not as dense as stars. And even though we're moving really, really fast, as fast as we might be able to as humans, some of these things move close to the speed of light. So there's different scales here. But that is the basic idea. Matter moving through space-time causes gravitational waves. And that's the basic message I really want to convey with this particular example. So one thing I would also like to talk about a little bit, and Abhinav in the planetarium show is going to explain a little bit further on where some of these objects come from. How do we get really dense objects like neutron stars and black holes, which are the densest things we think of? Well, stars are really dense. Cool. Stars have their own evolutionary life cycle. So they gain mass, they burn up stuff on the interior. Eventually they go into a red giant or a red supergiant, depending on their mass, their weight. And then they go supernova. Who here has heard of a supernova? Most people, right? They're cool. They're really cool. We like them. So yeah, they're hot actually, yes, okay. All right, you got me. All right, pack up, go home. I've been proven wrong. So supernova are what we call standard candles. They're super bright. They expel a lot of energy. And essentially, it's the explosion of this star at the end of its life. But not everything is just blown out in energy after the supernova. And the remainder will typically condense down into a very dense object. Depending on how much of that mass is left over, it might turn into a white dwarf, which, okay, that's not what we're talking about today, but if it's a little bit heavier, it might turn into a neutron star, which is what these things are. Or, if it's even heavier than that, it'll turn into a black hole. So that's where these super compact objects come from. They are essentially the graveyards of stars. So now we have a little bit of an idea of where these extremely compact objects, these really dense objects come from, as well as the gravitational waves that they create when they orbit around each other. Whoop. Oh boy, come on. Here we go. So our two-dimensional rubber sheet is a fine analogy. However, as I said, we are in space-time. So these gravitational waves, these ripples through space-time, look quite a bit different in reality. So what this is showing is an extreme exaggeration of what these gravitational waves would look like. So each green layer that's passing through is a ripple in space-time, a gravitational wave from a rotating binary of very dense objects. And it lengthens in one direction and compresses in another. So that's the whole idea of space-time. Space-time is our length, our width, and our height. When these things ripple, it changes the distances between these various dimensions. So it oscillates like this, or like this. But we're going to stick with this for now, because I can't move my hands in certain directions. It freaks me out. So not quite that coordinated. So in this particular illustration, it's lengthening in one direction and shortening in another, and then reversing. As I said, very exaggerated. This very, very exaggerated. If something like this actually hit Earth, Earth wouldn't be there anymore. So, but this is an idea of what would happen if when gravitational waves pass through the Earth. So how do we look for these gravitational waves? How do we find these ripples in space-time? This changing in distances in various dimensions? Well, what we do, and what has been done over decades of work and research and failures, is LIGO. Who here's heard of LIGO? Yeah, good. So LIGO is the Laser Interferometer Gravitational Wave Observatory. And they've actually been operational for decades, about 40 years. They came online, did some tests, didn't do so hot, went offline, tried to improve, came online, did some tests, didn't do so hot, went offline, tried to improve. Until 2015, when they finally did come back in line. And we're going to talk about what they saw in a second. But for now, let's just focus on the observatory itself. So we want to look for these ripples in space-time caused by matter moving through space-time, especially these really dense objects that are moving very quickly. So LIGO is trying to find this change in distance from these ripples in space-time. So how do we do that? Well, first off, there's one in Hanford and one in Livingston, Louisiana. So both of them together are considered LIGO. What they do, they have two arms that are perpendicular to each other. Each arm is 4 kilometers long. That's big. That's really intense. So long, in fact, actually, that they had to account for the curvature of the Earth when they were leveling them. It's pretty big observatory. So each arm is 4 kilometers long. One in Hanford, one in Livingston. And together, they try and locate and detect gravitational waves. So the reason why there's two is that if you see something in one, maybe it's a fluke. Maybe we didn't actually see anything. Having two and seeing something in both at the right time frame is a detection. So those are the two. However, we're actually forgetting one. And that's when one called Virgo comes in. So Virgo is part of the LIGO-VIRGO scientific collaboration, hence the name. And it lives in Italy. Now, because Italy is a smaller geographical country, but also very populous, there isn't as much empty space as there is in the States. So this one's only 3 kilometers long per arm. So together, all 3 of them were operational for a period of time this year. And they worked to try and find gravitational waves. So I've talked about a little bit about the history of them, where they are. How do they actually work? That's what we want to know. So what LIGO and VIRGO are Michelson interferometers, which means they use light, plain old happy light that we're used to, and they use that to make detections. That's the whole definition of an interferometer, using light to make detections. The Michelson interferometer uses mirrors and interference patterns to try and make sense of a detection. So what's happening in the sky, we have a laser, it bounces off the arms, it comes back, and if the arms are exactly the same length and nothing changes, laser goes out, hits the splitter, bounces up the arms, comes back. If they're exactly the same length, when the laser comes back, it will completely destructively interfere. What does that mean? What that means is that we get no residual laser light. Or we shouldn't. This is where I should probably mention that we do actually get a significant amount of noise in Michelson interferometers. Oh boy. Oh good, my PowerPoint stopped responding. Windows! Okay. I think it's just going to choke. I will continue to make the point, however. So with this Michelson interferometer, and because LIGO has been working on its sensitivity for so long, they're literally looking for the tiniest change in that laser detector. So actually, there are a significant number of noise sources. So we're bouncing off mirrors that are actually hanging on silicon threads. It's a really sensitive piece of equipment. Oh, good. So we do actually get a lot of noise in the Hanford and Livingston interferometers. And it can be things like people slamming doors. It can be things like transport trucks driving on a highway nearby. Which is also why Virgo in Italy, being right next to Pisa, has a lot of noise because it's right next to a huge city. However, there is one really good story about noise in the Louisiana detector. Has anyone ever been to Louisiana? A couple of people? Yeah? Yeah, maybe? Okay. So Louisiana is kind of known for having bayous or swamps, right? So where the Livingston detector is built is actually kind of in the middle of a bayou. When they were looking at the sensitivity of the Louisiana detector and trying to see what can we improve, how do we change this, what's going on with it, they kept seeing all of these really big noise spikes, and they had no idea what was going on. It was like, okay, it's not an earthquake, because we would have felt it. What is going on here? And it turned out that the Louisiana detector was picking up gunshots in the bayou. People shooting various wildlife. Out. No, out in just wildlife, actually. just the crocs, it's okay. just the crocodiles. I'm almost scared to touch it. Okay, so that's the point I wanted to make, is that they did actually have some issues with people shooting rifles and shotguns really close to the arms, and this is what was causing some of this vibration that led to noise. So that's why now you see in Louisiana they have this cleared space, and from what I last heard, there are fences up to keep people from going too close to the arm. America. All right, so that's the detectors. So what happens when a gravitational wave passes through one? Well, it should lengthen in one direction, shorten in the other, and then alternate, which means that our arms are changing length, which means that our lasers no longer completely destructively interfere. We should now see laser light in that detector. And depending on the strength of the light, how much we get in, depending on how the timing of it, will tell us if it's a gravitational wave or not. So that's how the Michelson interferometer works, and that's how we use it for detecting gravitational waves. All right, so everything I've shown you so far has been a ridiculous exaggeration of how big gravitational waves actually are. Just a heads up, we saw the video with the Earth and the stuff passing through it, and it's like, no, it's not actually that big. Earth would like fly apart if we had gravitational waves that strong. No, the Michelson interferometer isn't actually like moving this much. That's a little too strong as well. So how big is this distance change that we're looking for from gravitational waves? Really, how large is that detection? So to get a good idea of what it is, we're going to actually look at a hydrogen atom. So what I have here is a hydrogen atom. We have our proton in the center, and our electron zooming around in an electron cloud. And for those of you who have taken elementary chemistry and stuff like that, you should be pretty familiar with the idea of a hydrogen atom. So now we're actually going to go into the hydrogen atom. We're going to go in past the electron cloud, in towards the proton. Each grid is 10 times smaller than the previous, 10 times smaller, 10 times smaller, until we get to the edge of the proton, and That's how big these displacements, this distance movement is. That's the kind of detection we're looking for gravitational waves. From the most compact, from the densest, fastest moving objects that we think should be out there, that's what we expect to see. In numbers, that's 10 to the negative 18 meters. In relation to the proton and a hydrogen atom, it's about 1,000th the diameter of a proton. That's what LIGO was trying to measure. Now maybe we can understand why it failed so often in like the 90s and the 80s, right? It's a hard measurement to make. So now we have a bit of a better idea on what's going on in pictures like this. We know what the gravitational waves are, ripples in space-time. So because this detection is so small, because we have unexpected sources of noise like people shooting crocodiles in Louisiana, we need to know what we're looking for. We need to know what this data should look like. And that's where this waveform comes in, what we saw at the beginning. So what the waveform tells us is exactly what we should see in the detector. It gives us a template of the kind of data we should expect to see in LIGO. And that is how LIGO is able to confirm whether or not they've actually seen a binary black hole, a binary neutron star, or any combination thereof, by using these sorts of templates. So let's talk a little bit about the axes first. So time to merger, it's pretty straightforward in seconds. This one is strain. So strain is a way of talking about this change in distance that we've been talking about from the gravitational wave, this stretching and compressing. So 10 to the negative 21 is the strain we use. That is what translates us into 1,000th of a proton diameter. Frequency is how often we should see the gravitational wave iterating. How many cycles does it fit in a second? So that's what's going on here. So the Simulating Extreme Spacetimes collaboration, what I do as my research work here at the University of Toronto, and what a number of people do actually as well here as postdocs and as graduate students, is run these simulations, analyzes the data correct. Is that template okay? Does it make sense? Can we give it to LIGO? If we do give it to LIGO, what else do we need to do? What can we follow up on? And so on and so forth. For any and every combination of binary black hole or binary neutron star that we can afford to run on the computers here. And from all of this collaboratory work, from the LIGO collaboration in conjunction with the Simulating Extreme Spacetimes collaboration, providing them templates and ideas of what the data should look like, they found something. So this is the whitened data from September 14th of 2015, during LIGO, one of LIGO's many startup runs. This is what they saw. That kind of maybe looks like this, right? Can we see that? Kind of looks the same there in the center. Using the templates that SXS provided to LIGO and the many hundreds of people that work in LIGO, they were able to confirm that this piece of data that took about 40 years to find people's entire careers was indeed the first detection of a binary black hole. Pretty miraculous, to be quite honest. We did discover that this particular binary black hole was about 1.4 billion light years away. The two black holes that made this signal, this tiny, tiny signal, 1/1000th of a proton diameter change that we can measure on Earth, were about 35 and 30 solar masses. A solar mass is the mass of the sun. So one was 35 times the mass of the sun, and the other was about 30 times the mass of the sun, and they're whipping around each other pretty darn quickly, and we were able to see them. So this, I probably don't need to tell you, but this was a really huge discovery. It was it was one of the first concrete direct tests of general relativity, Einstein's theory of general relativity, that was formulated 100 years prior. It was the first observation of binary black holes. It was the first evidence of stellar mass black holes on top of that. So we had thought we'd seen or we knew of other kinds of black holes. This was the first time that we saw stellar mass, ones that were kind of, sort of close to the mass of the sun. So not only that, if that doesn't impress you, this was also the smallest detection attempted and successful in science. Again, 1/1000th of the diameter of a proton. The smallest detection ever made. And it was also the most energetic event ever observed. From what we could tell by that squiggly line from LIGO and Hanford, was that about 3 solar masses worth of energy was dispelled out into the universe from the merger of these black holes. What that really means is that it was more energy than all of the light in the observable universe combined. That's what this showed us. More energy than everything in the observable universe combined. It's pretty intense. So what does the most energetic event ever observed in history look like or sound like? Well, we just saw what it looked like. But leading into the idea of black hole of gravitational waves being the sirens of the universe, we can actually find out what they sound like. Okay, so over 40 years of research, over 100 years of analytic research, the first binary black hole ever discovered, a bunch of detections going along with it, the most energetic event we've ever observed, and it sounds like a chirp. Good, it's nice. So that's where we get the idea of sirens of the universe. Now, GW 150914, which was the first one, which is the one we've been talking about the whole time, is just one of the several we've detected since. So each one is labeled according to the date. So this one was maybe we found it. We didn't have enough certainty to really say that it was a binary black hole, but the rest of these are confirmed. The Boxing Day event, and then 3 more in 2017. So binary black holes are almost boring, right? So it was this huge discovery, and we've made a lot of detections of it since then. So impressive, in fact, that the 2017 Nobel Prize in Physics was awarded to 3 very special individuals in LIGO. To Kip Thorne, Rainer Weiss, and Barry Barish. And the description on the Nobel Prize was for decisive contributions to the LIGO detector and the observation of gravitational waves. That's what the Nobel Prize this year went to. Kind of a big deal. Also, Kip Thorne, you might also know him from the movie Interstellar. He collaborated on that movie, just in case you need another reason to think these guys are really awesome and cool. All right, so those are the detections of binary black holes we've had so far. But those are not the only detections we've had. Did you see it? Did you see it? Yeah, we'll go back. One more. Did everyone see it? Yeah? All right, so this tiny baby down here is the most recent detection, GW 170817. And the first thing you think is, oh boy, all the way down there, hey? So this guy is a little different, and you might realize that compared to all of its brothers that were detected beforehand. So GW 170817 is a very different kind of detection. And for a number of reasons, which I'll go into briefly, we can say that it's definitely not a binary black hole. So now, these are all the LIGO-VIRGO detections, and they're gravitational wave objects, but they're not all binary black holes. So what is GW 170817, this tiny baby down in the bottom? So well, what we think it is a binary neutron star. And one of the ways we can tell that is how long we were actually able to observe it in the LIGO detectors. So this is the length and time of observed for all of the detections. So we have the big detection that we were talking about, the Boxing Day detection, the 2 in 2017, and then this one, 1708-17. And it keeps going. It keeps going. The rest of these are becoming quite flat, and it just keeps going. So the length of the detection, how long we were able to observe it. This also tells us a lot about the two objects that we observed in this detection. They're kind of small. They're really small, actually. They're a little bit larger than the mass of the sun. Okay, that's actually a little bit too small to be a black hole. So that's two of the reasons, and there are a few others, but those are the ones we'll stick to for now, of why we think this was a binary neutron star. That's the end of the detection. It was 55 seconds. One of the more enticing reasons why we think this was a binary neutron star is because other people saw it. Not just in gravitational waves, but also in light. So this is a big diagram that's in one of the discovery papers from LIGO in collaboration with a few other people. We'll talk about that in a second. And it almost makes no sense, right? Looking at this, you're like, why do we have all this crammed into one figure? And I think it's because they just wanted to do it. Nobody actually knows why. Not even the people in LIGO know why. But what's important here is that LIGO detected something, and then Fermi picked up on it in short gamma ray bursts, which is a type of light that astronomers use frequently to discover things. And because of this very close correlation, where it was in the sky, when it happened, we're like, oh boy, these are linked, everybody point. And of course, like when you're looking at light, you have to wait until nighttime in certain parts of the world and all this other stuff. But what's really important here is that we were able to see stuff from this event in every band of light. Every kind of light that astronomers have at our disposal, we were able to take some information from. Or if there was lack of information, that was also information too. Seems weird, but that is how it works. So because of all this, we were able to say exactly where it was, what galaxy it was in, the fact that it was a binary neutron star, and deduce a lot of very interesting conclusions from this particular event. So this is the paper that actually was released for this event. Because you might imagine, okay, well, telescopes take people to run them, they take collaborations to work on them, et cetera, et cetera. And for anyone who's familiar with scientific literature or papers in general, normally how they're done, it's like, okay, well, here's our title, Multi-Messenger Observation of a Binary Neutron Star Merger. Okay, good. And then normally the piece after it is your list of authors. Who worked on it, who helped, this sort of idea. That's not the list of authors. That's the list of institutions. That's the list of authors. So we had 4,000 authors, 900 institutions, and 70 observatories work on this discovery. The discovery, the follow-up, and the investigation. So it's actually kind of a funny paper. It's listed as 59 pages. 36 to 46 is the authors. 46 to 59 is the collaborations. However, what's important here that I'd like to point out are some of these circles, so the red and the blue. And this is the University of Toronto contribution in this 4,000 author paper. So the ones in red, the 6 there, are CITA and LIGO, so the people in the Canadian Institute of Theoretical Astrophysics who are also associated with LIGO. And one thing I would actually like to point out right now is that that's pretty much the entire gravity group at CITA. Except for me, because I'm not in LIGO. It shows the one gravity person who isn't actually a part of the LIGO scientific collaboration. Good, okay. Know a lot about it though. The other author cited here is from Dunlap, and they helped with the light follow-up of the event. So we kind of had a well-rounded contribution to this detection. It did take me a while to dig up everybody's name though. It's a long list. So what does that look like? And this is an illustration of who was actually involved in the detection of the binary neutron star merger. So the yellow is the 3 gravitational wave observatories, LIGO, Hanford, Livingston, and then Virgo. And all of the blue dots are the light follow-up. And they were all over the globe, as you can see. There's even one in Antarctica. Look at that, all the way down there. So we had 7 in space, and then the rest on Earth. This was a huge global effort. And we could not have discovered all the things we did about this merger without the help of every single observatory listed on that diagram. This is revolutionary. You might think that astronomers and physicists and scientists work together all the time, but that's not actually usually how it is. We compete to get the first paper out there. We have opposing theories. And a lot of the time, we not necessarily work on our own, but work in our own little groups. This was the first time we had multi-messenger astronomy. Going from listening for gravitational waves to looking for light counterparts, and doing so on a global and international scale of this magnitude. Huge. So, all right, what did we actually discover with such a huge collaboration? So, one thing I would really like to point out is that this was one of the only confirmed discoveries of something that we call a kilonova. So you might remember we talked about supernovas a little bit beforehand. They're huge explosions at the end of a star's life, give off a ton of energy, standard candles, super bright. A kilonova sounds similar. What the idea of a kilonova is, it's also a really big explosion. But this time, it's from 2 very dense objects merging together, i.e. neutron star mergers, which is what we found. So the first detection of a kilonova. So kilonovas are particularly kind of special. 1, because we don't see them very often, or ever, depending on who you ask. And 2, they are what we think they're responsible, and now we know they're responsible, for creating what we call our process elements. What that means is that they create heavy elements, the big ones. And I give you your periodic table. So most of the periodic table, we kind of have a pretty good idea of where it comes from. Maybe it comes from the Big Bang, comes from the burning up in the interior of stars. However, a lot of the bottom half of this table, we don't really know where a lot of it comes from, for at least to explain the amount that we see on Earth. So this kilonova that we found explained these elements. That's not 1 or 2. That's a big chunk of the periodic table, y'all. That's a lot of them. And one thing in particular you should notice with silver, gold, platinum, a lot of these like really expensive elements, we now know where they come from. And there were the jokes of, oh, just got to create a binary neutron star, get the gold out of there. Yeah, okay. Ha 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 ha. So huge discovery. We had some explanation for where these things might come from before, but not in the amounts that we see them on Earth and in other systems. So this was a huge explanation for a large part of our periodic table. Obviously, that wasn't the only thing we found. That's just the one that the media picked up on because gold happened to be a part of it. So one of the very few confirmed kilonova observations. That was a really big one. We had never really seen the merger of compound objects before, like neutron stars, and had a light follow-up. It was the confirmation of a kilonova as a short gamma ray burst source. So gamma ray bursts we see a lot in astronomy, and there isn't really a good explanation of why we see so many or what causes them. So the fact that we can say a kilonova is a source of a gamma ray burst is a big deal, because we can say, okay, well now we can put some reasoning behind these observations. As I just mentioned, it was the confirmed source of many of the heavy elements heavier than zirconium, which is the 40 element. It was the very first observation of the merger of a neutron star binary. So we had seen neutron star binaries before. You might think of the Hulse-Taylor binary, which confirmed that gravitational radiation is a thing. However, we had never seen the actual merger before. It takes a really long time for these systems to merge. So it was the first time we had seen one. It gave a stricter constraint on neutron star models. Neutron stars are funny things. They're, again, one of the graveyards of stars. And we aren't really sure how they work. What do they look like on the inside? How do they function? So by observing 2 colliding, we were able to get some constraints on what they might actually look like on the interior. It's pretty cool. We were able to put stricter bounds on the speed of gravitational waves because we saw light waves from it as well. Always good. Always trying to check back with good old Albert on his theory. However, the biggest one, in my opinion, is the beginning of multi-messenger astronomy. This collaboration using our ears for gravitational waves and our eyes for light counterparts. is how we're going to continue making big discoveries in astronomy. So now we've kind of covered most of the whole gambit. Binary black holes, the discovery, what gravitational waves are, and binary neutron stars, and also the beginning of a whole new era of detection using 2 senses instead of 1. So I'd like to leave you with a representation, what we think the merger of 170817, the neutron star, looked like as these 2 neutron stars collided and gave off all of their intense light counterpart. If you look this up from the NASA website, it has a really nice orchestra background on it. Yeah, it's like, whoa, I just didn't include it because it was a bit obnoxious. Good. So thank you, guys.
For Catherine. So well, the way we'll do this is, I don't know, do you want to pick out people in the audience? You can ask your questions, and then Catherine will repeat the questions so everyone can hear it, and we'll see how many we can get through
sure.
in a few minutes.
Yeah, sounds good.
You mentioned that the first confirmed binary black hole merger was the most powerful thing ever measured.
At the time.
At the time. And I guess the biggest thing is, but then there's no light emitted because they're black holes. You get such a weak signal. Where did most of the energy go when you have something that powerful?
Right, so that's a good question. So the question was, the very first detection of binary black holes that we saw, GW 150914, was the most energetic thing we had ever seen up until that date, and actually still, because it was the biggest one we've seen so far. Where did all the energy go? Like, why did we have such a small detection? Why is it only 1,000th of the radius of a proton, I guess, or the diameter rather? And the answer to that is the energy gets dissipated as it goes through. So not all of the energy is just like pointed at Earth. It doesn't just, whoo. It goes out in every direction. So what we see on Earth, we can trace back and say, yes, this is how much energy has been released. However, energy falls off as 1 over the square root of the distance away from it is. It dissipates and gets absorbed into the rest of the space-time. So the larger the volume out you're moving, the less energy you actually see. So that's why, being 1.4 billion light years away, we only saw a very small signal. That being said, the signal was actually like one of the strongest we've ever seen. But that's why they're so small in comparison to us. So I'm going to get a different person. Okay.
You said it's because it dissipates. I guess how much does it compare in terms of energy to other events far away in light observations?
Oh boy, so I don't deal with light observations, so that's kind of hard for me to answer. It doesn't really, so in terms of like what we actually see here on Earth, the energy that we see, it's very, very, very small, like super, super small. I don't even think it could compare to astronomy observations. But tracing it back to the actual event, that's how we can say it was the most energetic ever.
Thank you.
You're welcome. Any questions? Yeah.
On the same subject, is it now possible to go out to look at LIGO results and find things that you didn't, like, be able to tell from the results, that looks like another one, and it was when?
Okay, so the first thing is that LIGO results are public. They're only made public after a certain number of months of analyzation, because obviously LIGO doesn't want to release their data and then someone say, I found a gravitational wave, and LIGO is like, darn, we missed the uptake. So they do take some time to release it because they analyze it very thoroughly first. The other thing I should mention is that I did mention this quite briefly. The data is whitened. So it is filtered a significant bit because there's so much noise, and it's usually a lot higher than the signal itself. So it would be very, very difficult for not just other people who work in the area, but also anyone to actually find something that LIGO hasn't. So the data is public after a certain number of time, after like about 2 months or so, after the detection. However, the chances of someone finding additional gravitational waves in that data is very, very small, as this is LIGO's specialty. And it's not easy to find the data in the first place. Could you find something? Yeah, but you're going to have a lot of people look at you funny and try and reproduce your results, and chances are they'll find something wrong with it.
Also, I guess the dissipation is such that by the time you're looking, there's not much to find.
There's not that much to find, that's true. So that's why the question was, there's not much to find by the time you actually look, and that is kind of true. That was why it was so hard for LIGO to find stuff to begin with. is because the detections are quite small. The energy that we actually see or hear is not very much compared to what happened at the actual event that we can extrapolate back to. Yeah. Yeah. Does anyone have any questions in the back? In the purple shirt?
I'm just wondering if the really heavy elements that we like gold are being supernovas, is it just because the energy is so intense in those kind of supernovas?
Right, so the question was, what makes kilonova special for making these heavy elements? Why don't we see them in, say, supernovas or other kinds of interactions? And part of it is because of the nature of the interaction. So supernovas are from stars, right? Makes sense, they're from big red giants. And they do actually create heavier elements than what happens in stars. However, what's special about kilonova is that they're using dense objects. So remember that this is mostly from neutron stars. Neutron stars are completely neutron matter. It's just like a big mass of neutrons and protons. And really, because it's just this essentially huge atomic nucleus, it's like, 15 kilometers wide. When it breaks up, it has a better chance of creating these really large elements. But it is also part of the energy that is in that explosion. It is very massive as well. So it's kind of a little bit of A, a little bit of B with that one. However, I should also say that I'm not necessarily an expert on kilonova explosions. Yeah.
You said that as a result of this, we're learning more about the insides of neutron stars.
Yeah.
What did we learn?
Right, so the question is, what did we learn about the interiors of neutron stars? So it is part of the discovery. However, I should say that whenever you are looking at things that are theoretical in astrophysics, there's always going to be that one or two crackpot ideas. Always. You're always going to have them. And everybody knows that they're a bit crackpot and they're really way out there and we don't necessarily want to use those models. So what this detection said was that no, spins this high for neutron stars are not acceptable. No, masses this high for neutron stars are not acceptable, which then cut out some of the more crackpot models, specifically two of them. Not a neutron star specialist, I do mostly deal with black holes, but they were able to cut out two of the more extreme models for neutron stars based on what they saw. So it is part of the interior, but they weren't necessarily able to see the interior of it. They were able to extrapolate back about the interior from the data they saw about the more general characteristics. Yeah.
So there's two quick points. First is, the creation of the gravitational waves, the black hole mergers would be powerful. So what would the energy be like up close, like in the galaxy or solar system or whatever, what would it be like close to it? And the second is, since the gravitational wave detector detects gravity, how did they compensate for the fact that we're on a planet orbiting a star with other planets orbiting a star, and that's all gravity too?
Right, so the first part of the question is, okay, gravitational waves are super powerful. What does that look like close up, like say if it was in the solar system? And then the second question was, how do we account for the additional gravitational effects, like the gravitational effects of Earth and then Earth around the sun and then maybe even the moon on the Earth and stuff like that. So the first part of the question is it scales, right? So what we actually see is the amplitude. And I'm thinking most people are familiar with waves. You have a wave, how big this part is the amplitude. The amplitude scale is 1 over distance. So the farther away you are, so if you're half as far away, like if I'm half as close, instead of it being 1.4 billion years, maybe I'm 7.7 billion years, then the amplitude would be twice as big. And it would go like that. The energy, however, scales as 1 over distance squared. So if I'm half as close, my energy is 4 times as big. So it scales pretty intensely. So it has been done, like back of the envelope calculations, and if you're about 10,000 kilometers away from the merger of 2 solar mass black holes, so like each one is the mass of the sun, which is pretty small actually, for black holes, you would have gravitational wave effects on approximately 1 millimeter. So the idea was like, okay, you have an astronaut floating in space and he gets hit with one of these gravitational waves. He's 10,000 kilometers away from the merger of 2 solar mass black holes. As long as the spacesuit can handle it, you should be fine, but we actually don't know how humans would, hold up to gravitational waves. We don't have that data. We just don't know. nobody really wants to get that close to a black hole, because that's actually the bigger problem with it is that you're 10,000 kilometers away from a black hole. Spaghettification and all that, right? No. So the gravitational waves would indeed be much stronger, a lot more energy. However, your bigger problem is like the event horizon being 10,000 kilometers away. And the second part of your question, how do they counteract for, say, the gravitational effects in the solar system? So as we said, the gravitational waves and stuff from the heaviest, densest, fastest moving, potentially, objects in the universe are still so small. So the gravitational effects from something that's only the size of the sun or smaller, even though it's so much closer to us, are just negligible. For things like the rotation of the Earth and some pulls like tides, we know those variables really well. I mean, we've had them on the Earth like forever. Not forever, the Earth has a finite age, but you get my point. It's basically been since the dawn of modern science. So we have a really good constraint on what those look like. Good question.
So we'll take one more question, and then afterwards, Catherine, however long you want to stick around, people can come up and ask her questions. Maybe we'll just do someone who has a burning question, who like absolutely will just be so disappointed if you walk away without being able to ask that question.
What a sin.
I think there's someone here.
Yeah.
It's just, okay. Why do the arms at the LIGO have to be so long?
Good question. So you might remember my my graph of strain. So with the waveform, and it shows it in strain. So what strain actually is the change in the distance over the total distance that you're measuring over. So the strain is always going to be 10 to the negative 21 for as far away as we expect it to be. So the larger your arm, the larger the change in distance, which means an easier measurement. So essentially we made them as long as physically possible without A, breaking the NSF's budget, and 2, running into a city, and X, Y, Z, right? So they're 4 kilometers long because they're as big as we could make them, as long as we could make them. As I said, they're long enough that we actually do have to account for the curvature of the Earth. It's pretty long. So they're 4 kilometers long because that's as large as we can make them. The larger you make them, the better, because that means you can detect more, because your actual measurement is going to be larger.